All right, let's work on our first series example. So we're going to try to represent this series, n equal 2 to infinity of n times n minus 1 c sub n times x to the n minus 2 minus the sum from n equals 0 to infinity c sub n times x to the n plus 1 in one series. Oh, I want to move this back on top. Okay. So if that's my goal, I need those two things to be true. I need lower bounds equal, I need powers x equal, and neither of those things is happening for me right now. So I'm gonna go ahead and start by naming the thing that I'm calculating. And let's just go ahead and start in the form we're given. So I need my lower bounds equal 0 and I need my upper bounds equal 0. So maybe I would look at this and I would say, okay, well, if I move this lower bound down, sorry, I need them equal, not equal 0. If I move this one down to 1 and this one up to 1, then they would both match. So I could go ahead and do that. Like this. I'm going to note that when I plug in n equals 2 to my first series, I have like 2 times 2 minus 1 times c2 times x to the 2 minus 2 is 0. So whatever I write down here, I want it when I plug in 1 to get that same 2 times 2 minus 1 c2 x to 2 minus 2. So if I just wrote n to replace that n, then my first term would be 1, which is no good. So instead, I'm going to do n plus 1. Now, if I plug in my first value, n equal 1, I get 2. So same thing here. I want this to come out 1. So instead of writing n minus 1, I'm just going to write n. That way, when I plug in the first index, I get 1. C sub n gave me C sub 2 before, so when I plug in 1, I'm going to have to do C sub n plus 1 to get to C sub 2. And then x to n minus 2 gave me x0 before, so if I'm only plugging in 1, I need to do x to n minus 1. And all those things are going to match. The other way you could think about it is when I subtract 1 on my sums, I'm going to add 1 to every n inside. So when I do this n equals 0, take it up to n equals 1, I started with c0, x to 0 plus 1 power. So if I did cn, I would get c1, which isn't good. So I better do cn minus 1. That way when I plug in 1, I get c0, which is exactly what I want. Then x to n plus 1 is supposed to take me to x1. If I'm plugging in n equal 1, that's just xn. And that'll give me x1. So I'm good. In this case, on my sum, I added 1. I went from 0 up to 1. So then everywhere inside my sum, when I saw n, I took away 1. I did the opposite. And I hope you can kind of like remember that rule and remember this process for general series. And I'm just deleting all that extra stuff where I was reasoning through it so it looks a little bit nicer for you on the sheet, the steps so far. Okay. So great, my first terms match. I've rearranged these so they have the same lower bound. I feel really good about what I'm supposed to do. Except, I said that series have to have the same lower bounds and the same x powers. And here, my x's have the same power, or have different power. This one's n minus 1, that one's n. But I need them to have the same. Eventually, I want to write them in one series where I have a bunch of stuff times x to whatever power I choose. And then in your notes, I've picked that xn is the power to go with, so we're going to do that. So if I want to take this one to x to power n, I'm going to go ahead and think I'm doing opposite of what I just did. Before I took n minus 2 to n minus 1, took my n equal 2 to n equals 1. So if I need to take x down one more power, up one more power, then I need to take my index down one more power. Or you can think about it, this is 1 minus 1 equals 0. So if I want xn, then the first thing I plug in has to be 0. So I could have done that from up here. If I have xn minus 2, and I want to start from xn, then I need to take away 2 from this n, because I need to start from x0. However we get to that point, we're doing the same thing as before with shifting our indices. So now, this was 1 plus 1, this was 1, and this was c 1 plus 1. So now if I want to reach 2, I need to add 2 to 0, or since I went down on my index, I go up inside. My n becomes an n plus 1, and my c becomes an n plus 2. It's a little scrunched. Basically, anything I did to this n, I do to all the rest of the n's. Then, for my second sum, I'm already at x to the n, so I can leave it the way it is. And I forgot my up to infinity there. So I have my x to n's that match, but now my lower bounds are wrong. So in general, what you want to do is you want to shift to get your x's correct first, and then worry about your lower bounds. In this case, leading you down that kind of wrong path to start didn't matter, because we do just go down in those indices until we reach xn. But our reasoning was really that we were trying to get x's to match, not that we were trying to get the indices to match. So the way that I deal with this incorrect index is I say, okay, I really need this to be n equal 1 to infinity times n plus 2 times n plus 1 times c sub n plus 2 x to n. I need xn, so I can't change anything inside that, but it has to start from 1, because I need it to match this other one I have that already starts from 1. But my first term here is that 0 plus 2 times 0 plus 1 times c sub 0 plus 2 times x to 0. And my first term of this series is going to be 1 plus 2 times 1 plus 1 times c sub 1 plus 2 x to 1. It's not the same. But luckily, what I've written right here is exactly the same as my original series before I tried to change my index. So just like how we can expand a series to be all those different terms like we were showing when we were taking derivatives of y, if we have a series, we can break up the terms that don't quite fit the pattern that we need and the terms that start from the index that we do need. And then as long as we leave this somewhere in our equation, we're going to be okay. So this is just going to become that I have 2 times 1 times c2 times x to 0 is 1, plus my sum from n equal 1 to infinity. And now I can combine both of my series because they both start from the same lower bound and have the same power x. And when I combine them, all I do is I take everything that multiplied x and I add or subtract them however they were in the series. So here I have that n plus 2 times n plus 1 times cn plus 2 minus that cn minus 1. And then at this point, I've finished the problem. I combined my two series into a single series given by this. And I have this little bit of extra leftover term that I would have to deal with. But that's something that we'll learn when we're actually solving these as differential equations. So nice work on your first section related to series. I will see you in the next video where we talk about series as solutions to differential equations.